When we have a geometric sequence, one thing that we might like to do is we might like to find the sum of the geometric of all the terms added up. And another way to refer to that is a geometric series. So if we want to find out what all the terms in a geometric series add up to, it'd be nice if we had a little formula to do the work for us, especially if there was a lot of terms. And so before we start using the formula, we're going to go ahead and derive the formula for the sum of a geometric series. So first of all, the sum we're going to refer to as big S, and this will be sub n, and the little n is going to refer to the number of terms in the sequence or the series. Like we've looked at already, the first term in any series we're going to call a sub 1. And the way that you find all the other terms in a geometric sequence is you multiply each one by some common ratio. We'll call it r. So if our first term is a sub 1, then our second term would be a sub 1 times r. And our third term would be a sub 1 times r again, which is r squared. And then our third term is a sub 1 times r times r times r. Now, when we get all the way to the end, when we get to our nth term, it turns out that'll be a sub 1 times r to the n minus 1. And you may recognize that that is our formula for a sub n, that we call that the nth term. Anyways, this is how we would write out a generic geometric series. Now, what we'd like to do is find out what is the sum of all these terms, and just imagine that there was a lot of these terms, like 40 or 50. It would be a real hassle to have to add all of them together, to do all the math for each term and then add all 50 terms together. So what we're going to take a look at is one way to eliminate some of these terms. It's a little trick we're going to do. And the trick goes like this. What we're going to do is we're going to multiply the sum times negative r. And we've done this sort of thing before when we had systems of equations. When we wanted to get rid of some of the terms, we would use elimination. And we sometimes would multiply through by like negative 1. In this case, we're multiplying through by negative r. Negative r times s sub n equals, it's negative r times a sub 1. Now, I could have written it directly below here, but that wouldn't make much sense, because when I do negative r times a sub 1, I get negative a sub 1 r, which matches up almost perfectly with this a sub 1 r. And if I keep going, I get negative a sub 1 r squared and negative a sub 1 r cubed, and all along they all match, all the way up till negative a sub 1 times r to the n minus 1. Now, what happens is, when I go to multiply negative r times this last guy right over here, there's something funny that happens. I get this guy right over here. Okay. Now, for those of you who are wondering how that is possible, let's take a look and see what happens. So let's say that we have a sub 1. Actually, I'm going to make it even simpler. Let's say we have r to the n minus 1. And let's just say for the heck of it that we multiply that times r. Okay, r times r to the n minus 1. I want to remind you that a while back we learned that if we had something like x times x cubed, that would be the same as x to the 1 plus 3. In other words, we'd add the 1 here that we don't see, that's the exponent, to the 3. In other words, we add the exponents together. It might be more obvious. You might remember that we had like x squared times x cubed, and that definitely turned out to be x to the 5th power, which is x to the 2 plus 3. But if we see no exponent, we'll call that 1 and we'll add it to the other exponent. Well, in that case, that means that we have a little 1 here that's kind of hidden when we multiply this r times this guy right here. So if we multiply these two together, what we get is r to the 1 plus n minus 1. And what that turns out to be is the 1 minus 1 cancels, it's just r to the n. And so that's why when we take this r and we multiply it times this right here, we get this over here. And you'll notice that makes perfect sense because we staggered all of the terms in the second row here. They're all one further ahead than the terms in the first row. So it makes sense that our last term would go here, and because r times r to the n minus 1 is r to the n, we do negative a sub 1 r to the n. Okay, I just wanted to give you some background on how that second row turns out. Now here's the part that's really cool. What happens is, if we add all the terms together in the top row and the second row, what happens is this cancels with this cancels with this cancels with this, all the way out to here. These all cancel. The only thing that's left over is a sub 1 minus a sub 1 times r to the n. And then over here on the left, we have s sub n minus r times s sub n. So let's take a look and see what that looks like. In the end, what we get is, oh, by the way, you'll notice that when we have a sub 1 minus a sub 1 times r to the n, we could factor out the GCF and make that a sub 1 times 1 minus r to the n, and that gets us this right here. That's where that comes from. Okay, and then this same thing. If we have s sub n minus r times s sub n, that's the same as s sub n times 1 minus r. And that's where this guy comes from. Yay. Now, we'll finish it off by, let's go ahead and do some math and get s sub n all by itself. And when we do that, we'll divide both sides by 1 minus r. And when we do that, we get the formula for s sub n, which is the sum of a geometric series is going to be 1 minus r to the power of n, all divided by 1 minus r. Yay! Exciting! So now, if you know the common ratio and you know the number of terms, you can figure out the sum of the entire, oh, oops, let's not forget, sorry, very important, we also have to know the first term, and don't forget to put your parentheses in here. So there we go, parentheses, parentheses. So if we know the first term and r and the number of terms, we can figure out the sum without adding up a bunch of things. Lovely.